Welcome back. So we have two parallel plates, not the kind you eat your dinner on, but plates just referring to maybe like a strip of metal or a metal plate, and they are 2.2 millimeters apart with a voltage across them. Right? And a reminder, voltage is just a separation of charge. So between these plates, one side will be positively charged relative to the other, which is negatively charged. And actually we can draw in the positive plate because we know that the field lines are drawn from positive to negative, right? And now that bottom plate might actually be neutral, but relative to the top plate, it is negative. And part A asks us to show, so we need to show by a calculation, that the electric field strength between the plates is 6.8 times 10 to the power of 3 volts per meter. So great, they've given us the answer. Wonderful. We are looking for electric field strength, which is denoted by the symbol capital E. We are given a distance and a voltage. So how can we relate those three variables? Looking at our formula book, we know that the field strength is the voltage divided by the distance. And you can actually see that from the units there, voltage per meter. Volts per meter. And let's just substitute it in. So in for voltage goes 15, and in for distance, do we put 2.2? Not quite. Reminder, in physics and in science, we communicate with SI units, right? Our standard set of units. So 2.2 millimeters is actually 2.2 times 10 to the negative 3 meters, or 2.2 divided by 1,000 meters. Yeah. So whenever you see a non-SI unit, make a note of it, and maybe just above it, write the SI unit, and then we can cross this one out. So substituting in our SI unit for distance, 2.2 times 10 to the negative 3. And now that is a show, because we gave the formula that we're using, relating voltage and distance, we've substituted in the values, and we know that the answer is going to be 6.8 times 10 to the positive 3 volts per meter. And we can always verify that with our calculator, going run math, 15 divided by brackets, 2.2 times 10 to the power of negative 3, close brackets, enter. So that's 6,818, which rounded to 2 sig fig, 6,800, which has scientific notation, is 6.8 times 10 to the power of 3. So, checks out. And that, of course, is an achieved question. And let's move on. So now an electron is released from rest at the negative plate. Well, we know that the negative plate is down here. So here's our electron. And it accelerates towards the positive plate. Notice how it's going in the opposite direction of the field lines. Right? Negative charge experiences a force opposite the direction of the field lines, whereas a positive charge would go with the field lines. And we're asked to calculate the maximum speed of the electron as it reaches the positive plate. Alright, so before it is released, what type of energy does it have? Right, so it's a negative charge right next to a negative plate. So it's going to want to be repelled. So we call that electrostatic potential energy. So initially, the electron has EP, electrostatic potential energy. And then what's going to happen is that potential energy is going to convert to kinetic energy. So EK. And we'll use this relationship and conservation of energy to calculate the speed. So electrostatic potential energy looking at your formula book, see if you can find it. Electric field strength times the charge times the distance it travels. We have all of those things, so let's compute that. So E was given, and we also worked it out. 6.8 times 10 to the 3. Q, what is Q? Q is charge, and in this case we're looking at an electron. So that tells us that the charge is 1.6 times 10 to the negative 19 coulombs. It is a negative charge. However, for potential energy, it's like relative, so we can omit that. So let's put that in. Q 1.6 times 10 to the negative 19. And finally, D, the distance. Well, it asks us to calculate the speed when it reaches the positive plate. So how far has it traveled? Well, it's traveled the entire distance of 2.2 millimeters. So all of that times 2.2. A reminder, millimeters we want to convert to meters, so times 10 to the negative 3. Cool. And let's compute that. So EP equals, substituting in our values, 6.8 times 10 to the positive 3 times 1.6 times 10 to the negative 19 times 2.2 times 10 to the negative 3, which gives 2.3936 to the negative 18. 3936 times 10 to the negative 18, and units for potential energy would be joules. Oh, an E magically appeared there. Cool. Now, we're not rounding it yet. We'll round it at the end. Alright, so just keep that in mind. Save your rounding until the end. So what happens to this potential energy? So initially it has potential energy, and it converts to kinetic energy. So we know that kinetic energy, EK, is equal to half mv squared, and we know it's going to convert to the potential energy, which we just worked out. So that's 2.3936 times 10 to the negative 18. Alright, and we are solving for speed. Right, and kinetic energy relates mass and speed of an object. Do we know the mass? It's not given in the question, but the mass of an electron is given in your formula book as 9.11 times 10 to the negative 31 kilograms. Very, very light. So we can substitute in mass and solve for speed. And I'll just do a few steps in one. So I'll times both sides by 2. I will divide both sides by mass. And I will then also square root. So speed is 2 times the potential energy. Right? Multiplying both sides by 2 to get rid of the half. And then dividing it by the mass of the electron. And finally, that would be speed squared, but we want speed, so we square root that entire term. So, and conveniently, we have the potential energy from our last calculation. So I'll times that by 2. So that's the numerator. I will divide that all by mass of an electron. Uh-oh. What did I do? Do you see what I did? So when I went for the negative, I did a double negative, so that made it a positive, which we definitely don't want. So let's try that again. 2 times 2.3936 3936 times 10 to the negative 18, so that's the numerator, all divided by 9.11 times 10 to the power of negative 31. There we go, and that is all square rooted. So shift x squared to get the square root, and then shift minus at the bottom to use the previous answer. Execute gives us our speed. So what's that? How many places is that? Looks like millions, 2.3 million. And so here's where we can do our rounding. Looking at everything that's given, looks like 2 significant figures is the lowest level of precision. So I'll round our answer to 2.3 million, so times 10 to the power of 6 meters per second. Right? Or if you want to be fancy, 2.3 mega meters per second, but that's not a very common way of expressing speed. Alright, and that is a merit question. Quite a hard merit question. It's usually paired with an explain question for excellence. So just to recap, we found the potential energy at the negative plate, E times Q times D. We equated it to kinetic energy, and we rearranged and solved for speed. Alright, a student states that increasing the distance between the plates while keeping the voltage the same will mean that an electron released from rest at the negative plate accelerates over a longer distance. Okay, that is true, and will therefore reach a higher speed than in part B. Now, they're asking us to use physics principles to explain why it's incorrect. So, it is definitely accelerating over a longer distance. That is true. However, it is not accelerating as quickly. Now, how can we explain this using physics principles? We could start with the equation from the first question, relating voltage and distance to the electric field strength. So if we increase the distance while keeping voltage the same, the electric field strength will decrease. Right? It's not as strong. And that means the electron will experience a weaker force and it won't accelerate as quickly. We could also use E subscript, P is E times Q times D, right? The electrostatic potential energy. And we know the electric field strength, E, is actually just V over D. So let's replace that, V over D. And you'll notice that these distances are actually the same, because it's the full distance of the plates. So they are the same distance, so we can cancel them. And we're left with V times Q. Now, this is telling us that the electrostatic potential energy does not depend on distance. So changing the distance does not change the amount of energy we give to the electron. And if we don't give it any more energy, well, it's not going to get any more kinetic energy, so it won't go faster. So let's put that into a few bullet points. So, electrostatic potential energy at the negative plate is independent to distance, or independent of distance. Great, so what does that mean? This means that the kinetic energy will be the same as in the previous question, Hence, speed or final speed will also be the same. And that is a merit question. Alright, and part 2, state one thing that could be done to increase the maximum speed of the electron. So going back to this argument, we know if the electrostatic potential energy is increased, kinetic energy will increase. So the thing that we can change would be the voltage. Right? We can't change the charge of the electron. Of course, we could send something with more charge through, but that's not increasing the speed of the single electron. So let's put that in. State one thing. Well, it does just say state one thing, so we could literally just write increase the voltage. Yeah, and this is again by this argument of electrostatic potential energy is VQ, and so increasing V will increase EP, increasing EP will increase EK, which will increase speed. Yeah, but again, it just says state, so you could say increase the voltage. And that part 2 is actually linked to part 1 for the overall merit. Alright, part D, our excellence question. We are given an electric field between a set of parallel plates. Okay, so it's a different scenario. They've given us D and V, just in terms of the variable of the symbol. And we're told the distance is doubled, but the voltage is halved. How will this affect the electric field strength? So, electric field strength, voltage over distance, we know that. So that is the current field strength, because we have voltage and distance. But what's going to happen if we double the distance? Let's just think that for a second. If we increase the distance, what's going to happen to the field strength? It will decrease, right? In fact, if we doubled the distance, it would halve the field strength. So say doubling distance halves field strength. Alright, now let's consider voltage. If we halve the voltage, or if we decrease the voltage, just in general, what's going to happen to the field strength? It will also decrease, right? Because they are proportional. Voltage is in the numerator, so if the numerator decreases, the field strength decreases. In fact, if it exactly halves, the field strength will also halve. So halving voltage halves the field strength. And so what's going to happen if we do both of these simultaneously? Well, we'll halve it once and we'll halve it again. So the new field strength will be a quarter of the original. So we could say new field strength will be 1/4 of original. Right? And the question does say your answer should include a number, right, or a ratio, and that's what we've done. So that's one way to think about it. Now I'll show you the maths approach. And actually, just before that, letting you know in this question, D, it does have 2 parts, but if all as you said is the electric field strength is 1/4, you would get excellence. That is an interesting E. For an interesting question. Yep, that's all it needs. Right, so part 2 only contributes to merit, which we'll get onto in a second. Alright, but you want to hear the maths method. I know you do. on the edge of your seat. So let's do that. So I'll use a different color. So our new E is replacing voltage V with half V, right, or V over 2, and replacing distance D with 2D. Now that looks a bit messy. We have a fraction in the numerator, but we know that we can write V over 2 times 1 over 2D. Right? If we have a fraction divided by a fraction, it's the same as the numerator fraction times the inverse of the denominator fraction. And that's more simply written as voltage over 4 times D. Now how does this compare to that? Right, they're both V over D, but in this case we have 1 over 4 or a quarter. So the new field strength is a quarter of the original field strength. Right, and that's the ratio method. Alright, now part 2. Using the same scale, draw in the field lines on the diagram to show the new electric field. Okay, so the same scale as this. Now what tells us about the strength of an electric field? Is it which way the arrows point? No, right? It's how close they are together. So if we wanted to double this field strength, we would put in twice as many arrows, like so. If we wanted to halve it, we would remove half of the field lines. What do we want to do in this situation to show the new electric field? Well, we said the new electric field is a quarter of the original. So we're going to want 1 out of every 4 of these field lines. So they've given us the edge or the side field lines. So that's 1 out of 4. Then we keep this one, remove the next 3, keep this one, remove the next 3, and then we should have 1 on the edge. So about that spacing. Now if you have your ruler, you could be a bit more precise. So how many did we say? Oh, and this one's, is it narrow? Are these in line? Oh yeah, pretty much. So what do we want? About 2 in the middle, right? A little bit off, but pretty close. So let's draw 1, 2. And if you're not confident in your drawing, you could always just describe what you mean. Now in this case, the mark scheme actually just has 1, which, yeah, it's between 1 and 2, right? It's kind of hard. So whatever you go with, it's fine, as long as you justify. So field lines, more spread out. Approx 1/4 of them compared to the one above. And there we have it. Now, just to recap this one, part 1, this ratio one, was the excellence part of the question. But for merit, if you weren't as precise, but you just said that the field strength decreased, but then you did give a less number of field lines here, being parallel and even, you could still get a merit. Alright, that's it. Cheerio.